And as you know, the whole trimester is dedicated to Elizabeth Meckes, who so tragically passed away this past December. And Elizabeth received her PhD at Stanford with Persi Diaconis, and we are honored to have Persi speak now in memory of Elizabeth. Please.
Thank you, and hello. What I want to do today is to talk to you about the interactions I had with Elizabeth, and in particular with focus to what she was going to talk about. I think she was supposed to give a short course at this school, and the title was Random Matrices, and so I'm gonna now, if I can find my slide again, and let me tell you how I met Elizabeth. So I was teaching the first year graduate course in probability, and at Stanford that's a big thing. 80 to 100 people take the graduate course, and I've been teaching graduate probability for a long time, and I was trying to think, what should I do that's new, and what's the most important thing that's happened in the last 50 years? And one of the most important things is Stein's method, and at Stanford, talking about Stein's method seemed like a natural thing to do. And so I stuck Stein's method into the first quarter of the probability course, and the way teaching probability is structured, we don't have conditional probability in the first quarter. We develop the measure theory and laws of large numbers and central limit theorem, but there's no conditional probability. And doing Stein's method without conditional probability is silly, but I managed. And but afterward, I felt awful, and because it's the wrong way to do it, and I decided I was going to run a seminar and try to teach people Stein's method the way it should be taught. And I took the two smartest kids in the class, and they were Elizabeth and Saurav Chatterjee, and the three of us ran a seminar on what Stein's method should be like. And let me tell you the story just for a second, and I have to get this to work, but there are many ways to use the idea of Stein's method, but the way that Stein thought was most central was what's called the method of exchangeable pairs. And Stein had developed that for the normal distribution to some extent, but he never worked it out for the Poisson distribution. So I decided we would focus on that. So just to say something, if W is a random variable, which is a sum of binary indicators, I is some index set, so xi are 0 or 1, and suppose the average value of W is lambda, what you want to prove is that the chance that W is contained in a set A is well approximated by the Poisson probability of A. And the method of exchangeable pairs takes W and builds a second random variable, W prime, where W prime and W are symmetrically distributed. They're exchangeable. And usually that's done if you have permutations or balls and boxes by making a small change, make a small random transposition or something like that. It's usually very easy to build an exchangeable pair. And then one of the theorems that came out of this work was this quantitative form, the chance that W is contained in A minus the Poisson probability of A was bounded by some expression, and there are two terms that you have to get your hands on, and they're usually easy to get your hands on, quite reasonable to get your hands on. And this was a new result. It's still, I think, the only place this kind of result is written out. Paper was didactic, and we had 30 students coming along, and we illustrated for the standard problems of elementary probability, the birthday problem and many variations, and coupon collectors and the matching problem, and we proved a version for Poisson process approximation. And if you want to look, it's one of Elizabeth's earliest papers. It's a paper we wrote it all up together, exchangeable pairs and Poisson approximation. And one reason for beginning with that story is how I got to know Elizabeth, but I'm fond of saying that nobody understands Stein's method. And Elizabeth just wouldn't have any of that. She said, no, the reason it works is this. And I thought, you young whippersnapper, how dare you? But she persevered. And if you look at the beginning of our paper, there's her explanation of why Stein's method works, and it's not bad. She didn't like loose talk, and she also wanted to be heard, and she was. So then she said, well, is there something to do? And so let me, at that time, I think I was doing random matrix theory, and so let me segue into that. So the orthogonal group is a familiar object, the set of all n by n matrices, where matrix times its transpose is the identity. These are real matrices. And anybody who studies mathematics learns that compact groups, like the orthogonal group, have an invariant measure, Haar measure. That is, it's a probability measure such that the measure of a Borel set A is invariant under translation. If I multiply A shifted by M, it doesn't change the mass. And that's nice, but the usual proof is all abstractified, and because it's true quite generally, and it's not so easy to understand what Haar measure really is. And let me try to just say this sentence in the way I'm sure that I said it to Elizabeth when we were talking, which is, here's a good way to understand Haar measure. Take an empty array, an n by n array, and fill it out with independent picks from the bell-shaped curve, IID normal 0, 1s, okay? And now do the Gram-Schmidt algorithm. Make the first row have norm 1, take the first row out of the second row, make that have norm 1, take the first 2 rows out of the third row. What you're left with is an orthogonal matrix because you made it orthogonal. And that's Haar measure. That's a way of picking Haar measure on a computer. And it's a way of working with it. And so that's what I just said. If you have a matrix of independent Gaussians, standard Gaussians, and you do the Gram-Schmidt, that's it. At some stage, work that I did with, Chuck Newman, and I was trying to understand Haar measure, and for Colin Mallows, that's right. So pick a random matrix from Haar measure and look at its trace. And if you have probabilistic leanings, the trace is the sum of a lot of little things, and they're not too dependent. And if you take the sum of a lot of things that are not too dependent, it should be normally distributed. And we showed that if M is distributed according to Haar measure, then the trace of M is approximately standard normal. And it turns out that the approximation is remarkably good. And in fact, an early theorem that I proved with Shashahani is that the moments of the trace, so on the left is, I'm averaging over the orthogonal group and taking the kth moment, equal, not asymptotic, not approximately, equal the moments of the normal distribution as long as n is sufficiently large for k between 0 and 2n plus 1. All the moments are equal. There's no normaling. You don't have to subtract off. You don't have to divide, equal. So that shows that they're pretty close together, and we'll come back to that. And there was a question of trying to take this sort of fact and make something better out of it. And here comes Elizabeth. This is start of her thesis work. So Elizabeth and Stein's method. So at that time, Charles Stein was around Stanford, and he said, well, you know, you could use the method of exchangeable pairs. And his idea was the following: pick a matrix M from the uniform from Haar measure, and then make a second matrix M prime by just multiplying it by anything, because Haar measure is invariant. If you multiply M by S, if S is fixed, it's still Haar distributed, and S can even be random as long as it's independent. So make an exchangeable pair by picking M from mu, and then M prime is M translated by S. And he had the idea that you want M prime and M to be close together, so make S small. And then he said, well, you know, you're a mathematician. He used to tease me. And he said, you can pass to the limit as S goes to the identity, and then you could probably work on the Lie algebra. I don't know what he was talking about, but Elizabeth was interested. And I said, why don't you try to figure this out? And she did. And she just built it into a very, very beautiful theory, the infinitesimal version of Stein's method. And one of the theorems she proved very early on was this: if you look at the law of the trace and you compare it to a standard normal and look at the difference between those two measures in total variation, that's small. In fact, she showed it's smaller than any polynomial. So it's less than 1 over n to the 5th when n is sufficiently large. Later on, Kurt Johansen, in remarkable work, proved this inequality. There's an explicit constant C to something that's explicit, such that the trace of M minus the standard normal is this close to normal. So let me put in an Elizabeth sentence. If I were talking to you informally, I would have said the distance between the trace and the standard normal is less than or equal to constant over n factorial. Now, that's not what was actually true as this, but constant over n factorial is easier to think about. And of course, this is about the same. But anyway, Elizabeth just wouldn't have that. She said, but that's line. And okay, this is a theorem. And he proved similar theorems for powers, for the trace of powers, and we had proved with Shashahani that all the joint mixed moments are equal to the joint mixed moments of normals. And but Elizabeth took this idea and made a whole new development of Stein's method, and that was her thesis. There's Kurt Johansen, with one of his co-authors, did this for powers of the trace and joint mixed moments of the joint mixed moments. And then with one of his students, Clara, they've extended it to the other compact classical groups. So that was my first interaction with Elizabeth, and all of her theorems, by the way, had nice explicit constants, and that makes me happy. The first thing she did after that was also very interesting, and it's an open problem, but given that I have a lot of smart people together in this group, let me tell you about it. She made some progress on it. So this is a little story about Elizabeth and quantum chaos. So in English, it's this: take a rough domain in the plane, and I just mean something that's not a circle or not symmetric, you know, just doesn't have to have a fractal boundary, just some domain that's not too nice in the plane, compact domain, say. And let delta be the Laplacian on the domain, and with, say, Neumann boundary conditions, reflecting boundary conditions. The Laplacian has eigenvalues. 0 is an eigenvalue because the Laplacian kills constants, and then lambda 1, lambda 2, and up they go. And it has eigenfunctions. The jth eigenvalue comes with an eigenfunction. And I'll norm the eigenfunctions so that they have norm 1 and L2 with the uniform distribution on this domain. Now, here's what we're going to do. Pick a point uniformly in the domain. Take a large J, 100. Define a random variable, W, by applying the eigenfunction to the point you picked. So make the eigenfunction a random variable on the domain. So J is fixed. Pick a point at random. Conjecture, and certainly true, that has a normal distribution. That is, if J is large, under very, very mild conditions. Now, the proof that there's no proof of that, it's a conjecture. There's an enormous amount of computational evidence that that's true. And Elizabeth managed to prove some special cases using Stein's method of exchangeable pairs, her version of Stein's method of exchangeable pairs, by picking a point and then wiggling it a little bit and looking at W and W prime in that way. And if you want to see the literature and see what's known about it, I recommend looking at her papers. She didn't solve it, but she did, I think, more than almost anybody else up to today. Well, you always learn things giving talks. So that's my sentence. So here's another one, Elizabeth in ballet, and let me stop this share and just tell this story this way. Hello. So Elizabeth had a very theatrical style to her. When she came into a room, people knew she was there. It's not negative at all. She had an electricity about her, and we used to meet weekly. And one day she came to my office for our weekly meeting, and she was in her ballet outfit. She'd just come to class, but also she was still wearing a tutu. And she came in and she said, well, I have something to tell you. And she went to the board and she began to lecture at the board. Now, Elizabeth wasn't a very tall person. And so very often she was on point and writing with her beautiful writing. And it's just an image that I have of her that I won't forget, just doing very nice mathematics while wearing a ballet outfit in my office. That's part of Elizabeth's personality. She had a theatrical style about her, and it was wonderful. So now I don't want to leave. I want to go back, and we're supposed to do math. Now I have to remember where I was, and I'm going to guess I was here. Okay. So okay, that was an aside. Okay, no, there has to be a way of going forward. So Elizabeth's book. Elizabeth got fascinated by random matrix theory and became one of the world's experts on it. And she wrote a very, very nice book, which is called The Random Matrix Theory of the Classical Compact Groups. And she had a good feeling for the amazing corners of the subject, but also she developed it. And there's a clarity about her writing and her presentation and detail that I think will make it the standard place that I would certainly send anybody to learn about it. And I think she was teaching at Oxford while on sabbatical when the tragedy happened, and teaching seminar out of her book. And I want to tell you a math story about Elizabeth, but also talk to you about one of her favorite results that is beautifully said in the book. And this is a theorem of another former student of mine, Eric Rains. Okay, so of course, the story works for all the classical compact groups. So let's take the unitary group, UN, the set of all matrices such as matrix, matrix, star, the complex entries, matrix, matrix, star is the identity. And just to give you a feeling for the result, let's work on U2N, so U100. And this isn't a limit there. And pick a random matrix in the unitary group, and you can do it just the same way I did. Fill out your array with IID picks from the complex bell-shaped curve, and then do Gram-Schmidt. Then you'll have Haar measure. So pick a random matrix, say 100 by 100 matrix from Haar measure, and then square it. Well, it's still a unitary matrix. And the theorem is that its eigenvalues are exactly, not asymptotically, exactly like the eigenvalues of a random matrix in U50, and pick another independent matrix in U50 and take the union of those two sets of eigenvalues. So that's a special case of this theorem. More generally, if you cube the matrix, it's like the union of three matrices in UN over 3, UN over 3, UN over 3. And you have to be careful about rounding. So if I worked in U3N, I would be okay. And if you want to see a careful statement, I'll try to write it down. But more generally, if M is uniform, say now in UN, then the eigenvalues of the mth power of M are the union of the eigenvalues of littler matrices, independent little matrices, where MJ is uniform on N over 3. But of course, this is true for all M. And if M is bigger than the dimension, then you just have well, I say it here. In particular, the eigenvalues of M to the N, for example, are like in IID uniform points on the unit circle. So of course, the eigenvalues of random matrices are very, very structured. They repel each other, but if you raise them to a high power, somehow they become independent. Exact, and these are not limit theorems. This is exactly independent. And this is true for any compact Lie group, these kinds of Lie groups. Okay, so when I heard that, I said to Elizabeth, so I think she was visiting at Nice for a year with Mark and the kids. I said, so what that means is that you must be able to go backwards. Take N independent uniforms on the circle. There must be a way of taking nth roots of that to make our measure. And she said, oh, that's interesting. Now, I've said that sentence, there must be ways of taking nth roots to 4 generations of graduate students and co-authors. And nobody ever did anything with it. Elizabeth solved it. She figured it out. She said, oh, that's interesting. And then she just went and figured it out. So that's a story about Elizabeth that warmed my heart and still does. So if you want to learn about random matrix theory for the compact groups, it's a wonderful place to go. I have 1 or 2 other things I want to say. So let me say this to begin with. The field of, you might think after she wrote her book, what else is there to do? Well, the field has exploded in the last couple of years. And one of the developments is this marvelous work on what's called the Weingarten calculus, and Benoit Collins and Sasimoto and Jonathan Novak have just done amazing work. The combinatorics is tough, but it's about submatrices of big uniform, big random unitaries or other compact groups, and they have amazing control, and they can give formulas for all kinds of things we never thought we'd be able to touch. In principle, there's a book happening, but if you want to see beautiful, deep mathematics, try to look at what these guys are doing about the Weingarten calculus. It's just great. A second direction that has exploded in the last year or two is the way of describing random matrix theory. Instead of looking at the eigenvalues of random matrices, another coding completely equivalent is the coefficients of the characteristic polynomial. That is, there's a lot of ways of describing the conjugacy class of a random matrix, and the characteristic polynomial is one way. So you could pick a random matrix and form the characteristic polynomial, and there are coefficients, and because the matrix is random, the characteristic polynomial is random. And of course, John Keating and Nina Snaith have done beautiful work making the connections between the characteristic polynomial and the Riemann zeta function, just wonderful work. And Elizabeth treats that in the last chapter of her book. But since then, much more is known and true. And I won't try to tell it to you. I'll just tell you one thing that that fascinates me. So we knew, because we know about the joint distribution of the traces, and the coefficients of the characteristic polynomial are the elementary symmetric functions in the eigenvalues. We knew that if you take the coefficients of the characteristic polynomial close to, for low degree terms, the coefficient of x to the fifth, that'll be some nonlinear function of Gaussian variables, and we wrote it down. Yes, I don't know, work I did with Alex Gambard. But there was a question, okay, pick a random matrix, look at the characteristic polynomial, look at the middle coefficient, or coefficients that aren't near the edge. What are they like? And this crew, and there's two of them, there's this triple, Joseph Nash-Noodle, and I don't know the others, Elliot Porret and Nick Sim, and then separate development but friendly development by Yassin, has just done amazingly deep mathematics. If you look at it connects to all parts of physics and differential geometry and other things. It's beautiful work. They both have long series of papers, and so one reason for my telling you about it is I can just picture Elizabeth's delight at saying, there's more to do, there's more to understand, there's more to translate, there's more to make quantitative limit theorems out of, because a lot of this is limit theory without errors, for example. And neither of us like that so much. So the subject keeps going, of course, and wish she could have told you about it. I have one last story I want to tell, and it's a question I wanted to ask Elizabeth, and I can't, so I'm going to ask you. And here goes. Here's a question. The question is, how do we understand the high order contact between the law of the trace of M and the bell-shaped curve? I never saw anything like that. Error terms constant over n factorial. How can it be? How does it know? And I'm not being dramatic. I really don't know. There's an easier question, and there's been some progress. And so let me tell you the easier question. I'm just going to say it. So suppose that, of course, the permutation group is a compact group. It's a finite group. It's just a symmetric group. Suppose I have a random permutation matrix. So pick M, pick permutation uniformly in the symmetric group. Let M be the associated permutation matrix, and let W be the trace of M. Okay, that's the number of fixed points of the permutation. That's the first theorem in probability in a certain sense. I mean, it's certainly in probabilistic combinatorics. It was in Momore in 1708, and he proved that the number of fixed points of a random permutation, the trace of a random permutation matrix, has a Poisson distribution with parameter 1. It's a very good approximation. And I showed sometime that it's just like the orthogonal group and the unitary group. So W is the number of fixed points of a random permutation. The first n moments of W equal the first n moments of Poisson 1. That is, that the expected value over the symmetric group is equal to this sum. I wrote it this way: equal. And similarly, the total variation distance between the law of a number of fixed points and Poisson one is, and this is right. There's no missing constants in this. This is an inequality. How can that be? I mean, why is it true? Well, one way of thinking about that, if you're a probabilist, but I mean, that's not the only way of thinking about things, but I can prove it, but so you should be able to find the Poisson distribution and the number of fixed points on the same probability space. You should be able to build them together. So, and that's a theorem. That is, you should be able to couple them and build bivariate distributions with one coordinate is Poisson one, and the other coordinate is the law of the number of fixed points. It's a theorem that there is a coupling. Well, what is it? I mean, where is that coming from? So math says I should be able to couple them this well. And here's the best way I know, and so bear with me. I have an infinite collection of independent random binary variables. The ith one is 0 most of the time. It's 0 with probability 1 minus 1 over I, and it's 1 with probability 1 over I. So the first one is always 1. Okay. And the second one is 0 with probability a half and 1 with probability a half. But more or less as time goes on, they're mostly 0. Okay, so those are xi's. Now form this infinite sum. Let W be x1 times x2 plus x2 times x3 plus x3 times x4, and keep going. Right? And this x2 is the same as this x2. Right? Just form this infinite sum. Little theorem, my theorem, that is exactly, not asymptotically, not approximately, exactly Poisson one. Okay, that's the first part of the theorem. Second part of the theorem, look at this random variable, x1 times x2 plus x2 times x3 plus xn minus 1 times xn plus xn. Okay, and then stop. Okay. Little theorem, that's exactly distributed as the number of fixed points of a random permutation. And neither of these is so trivial to prove, but they're concrete statements. Well, that puts these two laws on a common space. And so I can take the difference between these two, but unfortunately the difference is, the total variation is something like the last term, and that's like 1 over n or 1 over n squared. It's nothing like 2 to the n over n factorial. So that's a coupling, but it's not the right coupling. So I'm okay. Now, there's been some progress, I believe, although it hasn't been written up, I think it's been written down, that Jim Pittman knows how to find this coupling for the trace. And it's the most strange thing that you ever saw. It's nothing nice like this if you consider this nice. Okay, but meanwhile, why am I telling you this? Well, this stuff that I just did here, I can do all that for all the compact classical groups and all the finite reflection groups. It must be true for the classical compact groups. So in a paper I wrote with Peter Forrester on the history of Haar measure, we showed the following. There's some random variables, I'll tell you what they are. And if you look at y1, y2 plus y2, y3 plus dot, 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 infinite sum, that's exactly distributed as normal 0, 1. And if you look at y1, y2 plus y2, y3 plus yn minus 1 plus yn, that's exactly distributed as the trace of a random matrix on the orthogonal group. And y is not a mystery, it's a certain beta random variable. If you pick a random matrix from Haar measure on the ith orthogonal group, and if you look at the 1, 1 coordinate, that's yi. Okay, and so y1 is plus or minus 1 with probability a half. Y2 is pick a 2 by 2 orthogonal matrix, look at the 1, 1 coordinate. Yi is, pick an I by I orthogonal, look at the 1, 1 coordinate. Those are the y's. And This is not such a trivial thing to prove either, but it's true, and it's true for all the classical compact groups. There's an analog of this theorem for all the classical compact groups. While this gets me a coupling, of course, I know that the laws are close together by analysis, right? This gets me a coupling. It suffers from the same problem that I was suffering from before. But what it suggests is that, and there are many other reasons for suggesting that, what it suggests is that the orthogonal group or the unitary, the orthogonal group is a fattened out version of the symmetric group. And there must be a coupling that realizes this, and maybe somebody could look at what Jim Pittman has done, or just think about it and find. Now, I know that if I would have told that to Elizabeth, she would have gotten that funny look on her face and said, "I'll think about it," and she would have. I can ask Elizabeth. I can ask you. One way of keeping Elizabeth alive is to remember the beautiful mathematics that she did and talk to each other about it the way she would have talked to us about it. Thank you very much. Give up.